All right, so this video is going to be on photoelectron spectroscopy and how you read the graph, as well as how you connect what you're seeing in the graph to the structure of the atom and Coulomb's law. So to summarize, what this is there are notes in here on Coulomb's law, but I'm just going to summarize them. You can look through the filled-in notes to see it, but these are the big ideas we're taking in to PES. So the greater the distance between the nucleus and the electron, the weaker the force of attraction. If the distance is the same, the more protons the atom has, the stronger the force of attraction. And that distance has a greater impact than the number of protons. This is going to apply both in looking at PES spectrums and then when we start to look at atomic radii. Coulomb's law applies in so many other ways, but those are the two ones that we're going to look at. All right, so with that in mind, just quick review with Coulomb's law. We want you to be able to apply those two ideas. So we are going to go with which element has a stronger attractive forces. All right, remember, protons make the attractive force stronger. So more protons, more force. But actually more important to that is more distance, less force. And we're always looking at the outermost electron, so the valence electron. So this is the one we're going to think about first. And then if the distance is the same, then we start looking at the protons. So let's look at barium and calcium. So the two pieces of information we always start with the number of energy levels. And again, we're looking at the outermost electron, so we're going to think about that valence level. So if you find barium on your periodic table, it's element number 56, and it has, for the number of energy levels, you're going to look to the far left. As we label our periodic tables, we have those numbers on the far left, and that's telling us the outermost energy level. So barium is 1, 2, 3, 4, 5, 6. So there are 6 energy levels in the outermost, or where the outermost electrons are. All right, we do the same thing for calcium. So calcium has 4 occupied energy levels, which means that's all we need. So we're going to look at this top one, that as you increase the distance, the force decreases. So we're looking for the stronger attractive force. The stronger attractive force is going to exist between the nucleus and the electrons that are only in the 4th energy level, because that's closer than the 6th. All right, let's look at chromium and copper. So chromium, we find chromium on the periodic table. Chromium is element number 24, which means it's in the 3D, like that's where it's electron, the last electrons you write for the configuration. But you want to remember that we're looking at the valence level. So anything in the D block, you always want to think about, okay, I probably need to think about something else besides the straightforward looking at the number to the left. So for chromium, there are actually 4 energy levels because it starts with a 4s. That's where the valence electrons are. Same thing with copper, 4 energy levels. So we actually can't just use the energy levels to figure out which has the stronger attractive force. So now we have to go to the number of protons. So if we look at chromium, chromium has 24 protons. Copper has 29 protons. So we go back to our scientific principle at the top of this slide. The more protons, the stronger the force. So this one is going to have a stronger attractive force. All right, argon and xenon, try it on your own and then start the video again when you think you have an idea. All right, so I'm going to look at argon. Argon has 4 energy levels. I'm just going to start abbreviating that as EL. Xenon has 6 energy levels. Wait a minute. 1, 2, 3, 4. Nope, argon has 3. Sorry about that. Argon has 3 energy levels, which means that xenon actually has 5 because it's 2 below it. All right, so because distance has a bigger impact than the protons, or sometimes you'll hear me say distance trumps protons, it's more important. So the stronger attractive force is going to be in argon. All right, now we're going to keep all these things in mind and kind of bring back electron configurations as we move to our next slide. All right, so photoelectron spectroscopy, or sometimes you're going to hear us refer to it as PES. All right, it's a technique that we use to gather, or whatnot, like us personally, but scientists use to gather information about electrons in an atom. So what happens is the atom is bombarded with photons, and some of those photons are absorbed and electrons are emitted. So this actually goes back to the photoelectric effect when you saw those electrons leaving the atom. So what we're able to do is we can calculate, knowing sorry about the coughing there, knowing the wavelengths of the photons that we're sending in, we can calculate the energy that they have, and then we can measure the energy of the electrons that are leaving, and we can use that. So here's what happens. So we want to go back to when we were working with the first part of the unit. We were looking at if you send a photon of blue light into an atom. All right, let's focus on an electron in the ground state. All right, so we send blue light in, and that light, if it does have enough energy, or if it's the right amount of energy, that electron might jump up to a higher energy level. It's in its excited state, but again, it can't stay in the excited state, so eventually it is going to fall back down, and when it does, it releases the blue light. All right, so what we're doing now for PES, though, is we're going to use photons that have a lot more energy. So ultraviolet radiation, possibly X-ray. So let's throw an X-ray photon at this and really get this electron out of here. So again, the X-ray has a very short wavelength, which means that there's a lot of energy being carried in, and that energy could be enough for the electron to completely overcome the attraction between the electron and the nucleus. So that electron can leave, and then we're able to measure the amount of energy it leaves with. So we're able to figure out how much energy, how much attraction, the force of attraction there was between the electron and the nucleus. All right, I want to make a more direct connection to Coulomb's law. So let's say we had an electron in the fourth energy level. All right, so we want to think about how strong the force of attraction is. So this arrow is going to represent the force of attraction between these two electrons. All right, and I'm going to get rid of my electron arrow leaving. All right, so again, I just want to focus on the force of attraction between these two to kind of hit this Coulomb's law home a little bit more. So I want you to think about which of these two electrons experiences a stronger force of attraction. Hopefully you are thinking that this one experiences a stronger force of attraction because it is closer to the nucleus. Because of that, now if we think about the amount of energy it would take to overcome that attraction, you need much more energy coming in order to get that electron, or so that electron has enough energy to overcome that attraction. So just keep that idea in mind as we're moving forward. All right, so here is a photoelectron spectrum. So we're going to give you this graph, and I'm going to go through what all the parts mean. So what we're looking at here is on the y-axis, we have the number of electrons. All right, that's pretty straightforward. It's how many electrons would be released given a certain amount of energy that was sent into the atom. So on the x-axis, a little bit more going on here. All right, so what this is the x-axis is the amount of energy required to remove an electron. So if we think back to that force of attraction, more force of attraction means that there's going to be more energy needed, or higher binding energy. All right, so then the other thing I want you to notice about this is look at the x-axis. All right, so if we look at the x-axis here on this left side, sorry, I'm trying to get my mouse to do what I want it to do. All right, so here on this left side, the number is the highest there. And on the right side, the number is much lower. So what that means is if we see a peak, and the peaks are going to look like this, If we see that peak on the left side, it means lots of energy was required to remove the electron, which means it's a core electron or it is closer to the nucleus. So you can kind of think of the nucleus as being right here. And then as you go further away from the nucleus, it requires less energy to remove it. So when you have peaks that are way out on here on this right side, this peak is going to be furthest from the nucleus. So it's nice because it lines up with the electron configurations that we've been using from our periodic table. So let's put one of these into practice and see what it looks like. All right, so we're going to start with just getting you used to what these look like. So we have two PESs. One is for hydrogen, one is for helium. All right, so right now you can ignore what these numbers are on the top. They're going to be there, but we don't really use them very much. So first thing I want you to notice is that they both just have one peak. So that's what this is known as. You're going to hear me refer to this as a peak. So they both have one peak. For hydrogen, that one peak is shorter than it is for helium. All right, the hydrogen peak is also, if I look at where it is, it's also a little bit further to the right, and then this helium peak is a little bit further to the left, and we'll get into that in the second learning target. But what we want you to do is be able to look at this and say, okay, well, the first peak I see is the 1s peak, because that's the lowest energy electrons. And in this one, there's only one electron. I'm getting that from how tall it is. So that the configuration of that would be 1s1. Helium, we know it's 1s2. So the first peak is the 1s, and this peak has a height of 2. So there are 2 electrons that it takes that much energy to remove. This actually also goes back to Coulomb's law when we said that every electron feels the same amount of pull from the nucleus. So that's what we're seeing here, is that they both those electrons, whether it's they feel the same pull because it takes the same amount of energy to remove them. All right, let's go to another 2. So helium and lithium. So now the difference is, again, same thing. We can have different heights, the height of the first peak is the same, but lithium has 2 peaks. So if we think about helium and its electron configuration, the electron configuration for helium is 1s2. Lithium is 1s2, and then there's another electron in the 2s1. All right, so hopefully you're starting to see the pattern of how you do these. The first peak you see, you read it from left to right. The first peak you see is going to be the 1s peak. And then if there's another peak, you can always assume that the peaks the orbitals are full before you go on to the next one. All right, so let's try another one. All right, so here's how we're going to assess you and what you need to be able to do. All right, we're going to give you a PES graph, and you need to write the electron configuration and then identify the element. All right, again, always start from the left to the right. So from the left, my first peak is always going to be the 1s, because that's the lowest energy. Then I've got a 2s, and it's a 2s2. I know that from here. I also know it because if there's an additional peak, I can always assume that it's a ground state electron, so each orbital is completely full. So now I know I have a 2p, but I have to, on my last one, I always have to think about how many electrons there are. So this is a 2p3 because that goes up as high as the 3, which means my electron configuration, 1s2, 2s2, 2p3, and then I can look at the periodic table and either add up the superscripts here, add up the 2, and the 3 to get 7 electrons, or I can just key in on, I'm looking for second row, P block, the third one in. Either way, however you think about finding it, you know it is nitrogen. All right, let's try the next one. All right, so go ahead, try this one. Stop the video and then pick it up again when you have it. So this one, 1s2, 2s2, 2p6, and then 3s. It's only going up to the 1, so that is my configuration. Again, you're using your periodic table to know the order of those, and when you land on 3s1, you know this is sodium. All right, so that is the reading PES spectrums for writing the configurations. All right, now let's get into if we want you to compare two PES graphs. All right, and this really goes back to a lot to Coulomb's law again. So let's start with just whenever you approach a new graph, you want to just identify what's going on. So we want you to look at the 1s peak. So we've got the 1s peak, the first peak. How do they compare? So we've got carbon here, and we've got nitrogen here. All right, so we're just going to start with saying what's going on here. So carbon, or actually I'm going to talk about nitrogen. Nitrogen has a higher binding energy than carbon. All right, and the reason I know that is because it is further to the left, which means it's closer to the higher numbers. So nitrogen, the 1s electrons in nitrogen, and in fact, any of the orbitals have a higher binding energy than carbon. All right, so using Coulomb's law. So whenever it says Coulomb's law, you need to talk about attraction. The force of attraction, or just attraction from the nucleus, that needs to get into your answer. And your knowledge of energy levels and protons. So we're telling you exactly what needs to be in your answer. So make sure you pay attention to that and use that in your answer. Explain the difference in the location of the 1s peak. All right, so I'm going to start with thinking about what I know about nitrogen and carbon, thinking about the energy levels. So they have the same number of energy levels. So that is not going to cause the peak, the binding energy to be any different. They have the same number of energy levels. All right, so that doesn't matter. So now I want to think about the protons. So the protons, if I look at nitrogen on the periodic table, nitrogen has 7 protons. Carbon has 6 protons. Okay, so this, when we're doing the PES spectrums and they're moving to the left and the right, that's going to have to do with the number of protons. So you want to think about, back to our Coulomb's law, we saw that as there's more protons in the nucleus, there's a stronger force of attraction if the energy levels are the same. So if energy levels the same, and again, that is very important that the energy levels are the same. More protons equals more force of attraction. I'm just going to write more attraction right now, which then means higher binding energy. All right, so that is going to help me explain why the peak for the nitrogen is further to the left. So they have the same number of energy levels. Nitrogen has more protons, so it has a stronger force of attraction. I just really like this phrase, force of attraction. Therefore, it has a higher binding energy. All right, because it's nice, because if the binding energy and the force of attraction have a direct relationship. If there's a stronger force of attraction, like if you think, always go back to magnets. Think about these like magnets. If two magnets are really the strong attraction between the two magnets, you have to put a lot of energy into separating them. Same idea here. Strong force of attraction between the nucleus and the electrons means more energy is needed to overcome that and separate them away from each other. All right, so let's go on to another example. All right, example 2. We give you the complete photoelectron spectrum for sodium. So we want you to draw an X above the peak that corresponds to the orbital with the electrons that are on average closest to the nucleus, and then justify your answer in terms of Coulomb's law. All right, so first of all, I want to think about closest to the nucleus. Again, you can think about your nucleus being on this left corner. So the ones that are closest to the nucleus are the first peak. Okay, but now we have to explain why using Coulomb's law. And again, if Coulomb's law is involved, you've got to talk about the force of attraction, or what sometimes you can refer to as the FOA. If you're a band person, you're used to BOA. All right, that's Bands of America. All right, so why is that peak how do I know that peak is the closest one? So the peak has the highest binding energy. So I'm starting with just the evidence from the graph. Okay, highest binding energy, which means it experiences the highest force of attraction. Or greatest force of attraction. I feel like that's a better term. So it must be the closest. And that's the Coulomb's law connection. Is we're talking about, in this case, it has to be the closest to the nucleus to experience that. All right, and then the second one on the graph, draw a peak or peaks corresponding to the valence electrons of magnesium. All right, so here's the thing. We need to think about magnesium. This is sodium. So you have to think about the differences between magnesium and sodium. So it's the valence peak. So I know it's going to be the furthest one out, but now I have to decide, is it going to be to the right of the peak, to the left of the peak, and how tall is it going to be? All right, so those are two decisions that you have to make. So sodium, I know, has 11 protons. Magnesium has 12. All right, so now that I have to use that information to decide, okay, is there going to be a stronger force of attraction, meaning a higher binding energy, or a weaker force of attraction, meaning a lower binding energy? So more protons means higher binding energy, or stronger force of attraction. Which means higher binding energy. Make sure I phrase that binding energy. All right, so that means to make a higher binding energy, I have to move it to the left. So I know it's going to be to the left. It's going to be closer than the one I have right now. Then I have to think about, okay, is it the same height or is the height going to change? We're talking about valence electrons. If I look at magnesium, so sodium ends with 3s1. Magnesium ends in 3s2, which means that there's two valence electrons. So for my peak, I need to draw it to the left, and I'm going to need to draw it a little bit taller. In fact, up to the 2. So where it is on the left, just scoot it a little bit to the left. You're not going to be able to determine how much to the left, but also you wouldn't expect it to jump over another peak. So just write it to the left or to the right. All right, and that is photoelectron spectrums, how you read them, and then how you interpret putting another element in and comparing different elements.